Hey everyone, we just finished looking at ray diagrams for lenses. Now we want to go ahead and bring in the equations so that we can get more exact answers when looking for the image location or its magnification. The great thing about these equations is that they're the same that we use for mirrors. The first one is the magnification equation, looks identical. Magnification is given by the image height over the object height, right? It tells you how much bigger or how much smaller your image is compared to your object. And it's also equal to negative Q over P. When you do a ray diagram for lenses, you get similar triangles, this blue and this orange one, that ends up relating those quantities and the ratios are equal. The other equation that is identical to the one we used before, we called it the mirror equation. Now we're simply calling it the thin lens equation. 1 over P plus 1 over Q equals 1 over F. So it relates those three quantities. If we have 2 out of the 3, for example, if we have the focal length and the object distance, then we can find Q, that image distance. Before we can use these equations, we do need to be careful about the sign conventions, what's a positive and what's a negative. So this image shows you here that if the object is in the front, P is positive, and that's going to be the case most of the time, that our image is going to be in the front here because our object is going to be in the front, the light is going to come from the left side. Now if you have a converging lens, you know that those rays are going to converge and your image is going to be formed over here. So if the image is actually formed in the front, then it's a virtual image and we're going to consider that a negative Q. So looking back at the back side of the lens now, if P is in the back, it's going to be negative, but we're never going to encounter that situation in our problems. But if Q is in the back, that means that the rays actually intersected there, so that will be a positive image distance. We have those same sign conventions summarized in the table here. So P, the object, if it's in the front, it's positive, in the back, it's negative. We're not going to really see this one. But the image, if it's in the front, it was virtual, so it's negative. But if it's in the back, it was a real image, and that's a positive distance. And then as far as the radii, we don't really use these. We look more at the focal lengths. You're not always going to be given that a focal length is positive or negative, so you have to use your knowledge. If it's a converging lens, looks like this, then it has a positive focal length. If it's a diverging lens, looks like this, it has a negative focal length. Let's go ahead and look at a problem that will draw a ray diagram, and then we'll also use the equations to see that they give us the same exact answer. So in this problem, it says that we want to see a flower better, so we're going to hold a length as a magnifying glass. We saw this earlier, that when your object was very close to a converging lens, so positive focal length, that the lens served as a magnifying glass. So let's go ahead and do this problem here. Let's use that each of these big lines here is going to be 4 centimeters. So this is 4 here, this is 8. So the object, it says the focal length is 6. So it's going to be in the middle here. That's going to be the focal length. Remember that for your lenses that you draw a focal length on each side. So we're going to have another focal point right here. So we have our lens drawn, we have our focal points drawn. Then we're going to draw the object. It says that we're putting it 4 centimeters from the flower. Doesn't say how big it is. We can make it however big we want. Since we know it's going to be magnified, we don't want to make it too big. So I'll make it 2 squares tall. It's kind of my default there. And now we are ready to draw our rays. So let's go ahead and do that. Our first ray is going to be coming in parallel to the object, and then it's going to refract. It's going to refract through the focal point on the other side. And since this is a converging lens, we can go ahead and write down my little shortcut that I like to use. So for your lens, for your converging lenses here, you have parallel on one side, focal on the other. You're going to go through the center, then you're going to have focal on one side and parallel on the other. So let's go ahead and finish this up here. So this was our first ray, our orange ray. Our second ray is going to go through the center and keep going. So I'll draw it straight through that center there and keep it going. There we go. You can see that the rays are diverging here. And then our third ray has to go through the focal point on the left side, but since the focal point is over here, we have to appear to come from that focal point. So we draw a straight line from that focal point, and then it then hits our object, so the light is still coming from the object, but then as soon as it hits the lens, then it's going to emerge parallel on the other side. So that's going to be that third ray right there, emerging parallel. So what we can see is that these rays diverged. So we have to trace them back to see where they would intersect. So let me go ahead and try to do that. I'll just use a black line, just ignore the arrow on the line. I'm just trying to trace these rays backwards to kind of see where they intersect here. So just trying to draw a straight line here. Then I'm going to draw a straight line, tracing this ray back. Again, ignore these arrows here. We're just tracing those rays straight back. I usually like to trace them with a dashed line, but haven't quite figured out how to do that with this application that I'm using. But we can see that when we are tracing these rays back, that they all seem to intersect at this point right here. So that is where our image is going to be formed. We always draw the line from the optical axis to where those rays are intersecting. So they're intersecting right here. So that is our image. We can see just by looking at it that it's bigger. It looks to be 6 squares tall, while the object was 2 squares tall. So it looks to be 3 times as big, so have a magnification of 3. So let's go ahead and take a look at the equations and see if we can get the same answer. So with the equations, we are given the focal length f here. F is equal to 6, and we're given the object distance p. It's a converging lens, so it's positive. Now we can find the image distance q. To do that, we're going to use the thin lens equation. 1 over p plus 1 over q equals 1 over f. And we've seen before that if we manipulate this equation to solve for q, go back to the mirror video and see the algebra done here, but we're going to get p times f over p minus f when we get q by itself. So now we can go ahead and plug in the numbers, see what we get. P is 4 times 6 divided by 4 minus 6. So we can see we get 24 over negative 2, which gives us a q of negative 12. So that makes sense because the image was formed in front of the lens. It was a virtual image, so it has a negative image distance. And now to get the magnification, we can use magnification equals negative q over p. So negative times a negative 12 centimeters over a positive 4 centimeters. Centimeters cancel out, right? Magnification does not have a unit, but the negatives also cancel out. So we get a positive 3 for the magnification, which agrees exactly with what we found. The image is upright, hence the positive magnification, and it's 3 times as big.